when was the last time you were at the gym?
I didn't know this was going to be a Senate committee hearing. I mean, damn. I was at the gym yesterday.
These guys are so funny, man, honestly. They just make you laugh. Chuck reminds me of Eddie Murphy. So funny. And you get to learn that Neil is a great teacher.
Hey,
Yes, I was.
nice.
I was.
So what's your regimen, typically?
I try to do cardio 3 or 4 times a week because of my condition. And
You have a heart that needs
I
that
have a
extra.
heart that needs that. And then
And this is on a treadmill?
sometimes a treadmill, sometimes a stair climber, and sometimes a bicycle. And then I try to lift weights a couple times if I can.
Is it dumbbells?
Yeah, dumbbells.
No barbell?
No, I have shoulder problems.
So you don't do bench?
I don't do bench presses.
So what Neil's trying to do here is he's trying to understand what Chuck's regime is in the gym, and see, he specifically mentioned bench press, and he's going to explain the science behind bench press, which is interesting because you never think about it.
If you just do dumbbells, you never need a spotter.
Well, it depends on how heavy the dumbbell
You know what I'm
is.
saying? But if you're lifting and it's too heavy, you just drop it.
That'll get you kicked out the gym in my gym. They don't allow it. But yeah, no.
Yeah, the
you don't
spotting-
really. No, spotter is definitely for the bar because if the bar comes down, it breaks.
Yeah, you die.
Right.
There's where spotters matter.
Absolutely.
Okay?
Yeah.
And I want to describe the physics of being a spotter.
All right. You do know that those people are not our core audience.
That is true.
I'm just saying.
I think we have a few.
I'm sure we do.
Okay. But whether or not you've ever been to the fitness center,
Right.
you've heard of spotters.
Yes, of
Okay?
course. Yeah. Yeah. Everybody knows that.
So let me tell you how
Not everyone, Chuck, I'm going to have to say not everyone would know what a spotter is unless you actually go to the gym.
forces work, if you didn't otherwise know.
Oh, even if I did know, I still want to hear from you.
Okay.
Because I probably would re-know it.
Okay. So first of all, you can't just engage a force without pushing against something.
That makes sense.
Okay, you can't just
Like
have a
even
force
walking.
in the middle of nowhere. Yeah, you're pushing against friction,
Right.
on the between the rubber of your soles and the
that side of walk, right.
Okay, and Earth is recoiling against your moving forward.
Yeah. Okay, I'll accept it, sure.
In proportion to your relative masses. Okay.
All righty. Now that's a big point. Right.
And this is one of Newton's laws: for every action,
Equal and opposite.
an equal and opposite reaction.
Okay.
Yeah, I
The
read
word
that.
force wasn't so fully conceived at the time, so you call them actions.
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 Yeah.
Okay. That's why, for example, flying saucers, can't
Yeah.
just move unless something gets pushed out the back.
Exactly.
What is that something? See, this is controversial, right? Because I don't think Neil believes in UFOs and aliens. Partly he's right because there is no evidence, but we've seen videos of flying saucers and nothing gets ejected. Like you can't see anything being ejected, right? For example, in a rocket or a plane, you can see, the fuel, which is the reaction that pushes the plane forward, right? But you don't see that in the case of UFOs. He picked an example of a UFO. I think that's the wrong example because you can't see it as far as UFOs are concerned.
Just can't
Yes.
send themselves into motion.
Right.
That is not real in this universe.
So when we see them hovering and then they go, pew,
Right, they could do that,
they
but
do that, but they would leave something behind.
that's why whenever you see rockets, there's something come out the back end.
Exactly.
Yeah, rockets we
Right, so
can, but
combination
UFOs
of
you can't
mass
see.
and speed gives you momentum to go the other way.
Gotcha.
All right. So you take all the forces operating on an object. Some will cancel out. If they're exactly opposite, they'll just cancel. Okay? But if somehow there's a net force, the object will accelerate according to that force.
Okay.
Another one of Newton's laws. Force equals mass times acceleration.
Okay.
If there's a net force, you're going to have an acceleration.
Gotcha.
Period. We together on that?
Well, definitely.
Okay. Does it make sense that the bigger the mass, the less effective a force will be in its attempt to accelerate the object? Because this is an equation,
Right.
right? And both sides have to equal.
Exactly.
So if I only have a certain amount of force and I'm pushing a bigger and bigger and bigger object, the acceleration has to get lower and lower and lower.
Yep, that makes sense. So it'll need more force for you to push a heavier object, and as a result, because it's heavy, the acceleration slows down because it has to compensate. That's what the equation tells us.
to compensate.
Right. Okay.
That makes sense.
And of course, vice versa.
Of course.
If all forces are in balance, one of two things are happening. Nothing is moving,
Right.
or it's moving at a constant velocity. All a force knows how to do is accelerate something.
Right,
So
right.
if all the forces are balanced, it could still be moving, just not
Just
accelerating.
accelerating. Okay.
Okay.
Makes sense.
Got that?
That's all.
Bit difficult for me to understand, but okay, yeah, it kind of makes sense.
Are we on the same page?
We certainly are.
Okay. If all the forces balance, I don't care how high they are. If I just add a little force that's a net force on top of everything, it's going to move where I put it.
That's right.
I push it, I can blow on it.
Right. And it will move.
Okay?
Absolutely.
All right. Let's go to the gym. For any weightlifting where you could die if you lose your grip or your ability to support it, you want a spotter. Okay?
Yeah.
Okay, so now, the
Okay.
bench press is the most common example of these.
Right.
Bench press, you are flat, a horizontal plank. Often the back can go at different angles.
incline
but
or
let's
not.
look at the limiting case. It's flat.
Yeah.
Adjacent to each side are two little holders. And you have a barbell across the holders.
Right.
Distinct from dumbbells, which are one you'd hold in each hand. Okay, those are called
Individually
dumbbells.
hold them, right.
Okay. Barbell, weights on each side.
Okay.
Okay?
Yeah.
I'm pushing it up. And I'm strong man. And I'm not just doing reps where
Right. No, you're lifting heavy weight.
heavy weights.
Yes.
You can do reps that does a different thing to your physical musculoskeletal structures than if you lift very heavy weights.
Right.
If you do reps, you'll get good toning of your muscles. Very heavy weights, you actually damage your muscles, and then at the end, the muscles are rebuilt to be bigger and stronger.
That's right.
If they
Wow.
get
That's
the
true.
bar above the two little hooks,
Right.
and they can't struggle with it, they can just pull it back onto the hooks.
Right.
Because the
Right.
hooks are not at the limits of your reach.
No.
They're somewhere in the middle, and then you go, and then you come down to your chest.
Right.
Here's the scenario. I got it on my chest, and I'm pushing it up. It's like my third or fourth rep of some of the heaviest weights I've ever lifted. I reach a point not high enough to
get
deposit
onto the hooks.
to get on the hooks.
Yeah, that's
And
happened to
I
me.
can't push it anymore. And I can't get it, but I want to because I don't want to be girly, man.
Right.
Okay? And so I got to do it, and people are watching me. I can't. All right. So in comes the spotter. Spotter can take a single finger and just lift it up.
Right.
Wow.
You know, I've never tried this, so yeah, I've got to experiment this, but maybe he's right. You know, it just takes that much force, like a finger, to just put it back in place.
Because all the forces have
Balance
balanced.
in that moment.
Yes. And so now all you need is
There's one little extra net force.
this little nerd just comes with his finger and he's boom.
There it is.
And he can help you lift
That's
it all
all
the way
it
up.
takes. They get to a point where they can't push it
okay.
any further. Everything is
That's
balanced
the sign.
in that instant.
Must be right.
Any force will lift it.
Will lift it.
Yeah, and they want to help you too. They're there
Of
to
course.
still push.
Right.
So that's why a way skinnier person can spot for
for
very
the guy
very
who's
strong
lifting
people.
tons of weight.
It's vast.
Oh, rainbows. Interesting.
It's things that
We've all seen
you already
rainbows.
see in your world, but maybe I can boost your appreciation for it.
Oh.
That,
all right.
That's the goal.
That's the goal.
Okay, I love rainbows.
No, but that's just, you can't help but love
I
rainbows.
can't help but love rainbows. But it was not until Newton who figured out that those colors are in the white light from the sun. People thought the raindrop put it in somehow, okay? Or the crystal, because sometimes you can see crystal
As it passed through
As it passed through.
It imbued it with color.
imbued it with color.
Right.
Right.
Why would you think
Yes.
that white light has red, orange, yellow, green, blue, and
True.
violet in it?
Yeah, I wouldn't think that. Yeah, that's true, right? Yeah, white light is white light. There's no different colors within that light. It's just one color.
Wouldn't.
But Newton,
Right.
he's different.
Because he is, he sees the world differently.
Yeah, but it's white light from the sun,
Right.
coming through a raindrop, and it refracts. Refraction is simply the bending of light. Then it disperses. You take all the wavelengths and you spread them apart.
Apart. Okay.
Because white light is composed of many wavelengths.
Yes.
All colors.
Right.
Okay. And so there's your rainbow. Okay. Some fun.
If you never experimented, just buy a prism and do it. You can do it at home. Just buy a prism. You can get it on Amazon or eBay. Really cheap. Just next to your window. You just put it next to your window where there's strong sunlight, and then you'll see the rainbow effect coming off the prism.
Facts about rainbows,
All right.
if I may.
Please do.
Okay. So let's get the colors straight. Isaac put in a seventh color because he had a mystical fascination with the number 7. To normal eyes, it's got 6 colors.
Okay.
Red, orange, yellow, green, blue, violet. And those are the 6 colors on the original Pride flag. So, Newton said, I want some 7 in this. So guess what he did?
Go ahead.
He added indigo. Red, orange, yellow, green, blue, indigo violet. Okay?
Gotcha.
If you leave out indigo, no one will fault you. But if you keep it in, you get to pronounce the name of the person who those letters spell.
Roy G. Biv.
Roy G. Biv. That's how I remember the sequence.
Who's Roy
red,
G.
orange,
Biv?
yellow.
Right.
I don't know any Roy G. Biv. Is that a scientist? Who's Roy G. Biv? Let me know in the comments.
G, his middle initial.
Right.
Biv, B-I-V.
Right.
There you go. Here's something that I think either people don't know or they don't appreciate. It is a complete optical phenomenon. The rainbow is not in any objective place in the sky.
Okay.
It's an optical phenomenon for you. Someone standing next to you,
May not see it.
they see a different rainbow.
Really?
Everybody sees their own rainbow.
This is
The rainbow looks identical,
right.
but it's just your own rainbow.
Right.
Okay?
Oh, that's cool.
Now, think
didn't
about
know
what
that.
that means. It means you can't say, let me go around the backside of that rainbow.
Right.
Because it doesn't exist
Yeah.
as a thing.
Yeah.
You've never seen a rainbow at some kind of angle to your view.
Correct.
It is always frontal to your sight line. They all have a
Is it?
diameter of about 80, between 80 and 85 degrees. Okay, a diameter at the maximum arc.
Right.
Often you see less than the maximum arc, so it doesn't.
Okay, so I have seen rainbows at an angle. You don't have to be able to see it front on. You can see it from a side angle. I think that's what Neil is saying. There's at a certain angle you can see it, but beyond that angle you can't see it.
Up this large. If you see a full half circle rainbow, it's like 80 degrees across.
Okay.
Every
Okay.
rainbow is that size.
Right, okay, so what I've seen is maybe within this region, this radius of 80 degrees. So if I were to step out of that 80 degrees or angle, I'd probably not see it or not be able to see it. But if someone else is within that radius, they'll see their own rainbow. Okay, that kind of makes sense.
That's cool.
Everyone.
That's very cool.
If you're watering your lawn and the sun is the right angle and you see a rainbow, it will have that angular size.
Think that our laughter has evolved from when you see them cackle like that.
Oh.
Like it's something from our common ancestor.
So that sound that they
That
make
sound.
and our sound of laughter.
As us. This is Natasha Shaw Davis. Eyes see some wiggles in matter, and ears hear a little more. But the whole body experiences gravity. If you could pick any organ to deliberately experience the graviton, what would you pick?
My heart.
Oh,
My heart has its requisite number of beats per minute.
right.
And it goes up when you get excited or
Yes.
you exercise,
Okay.
and it calms down. So the heart is with you in your emotional moments.
Correct.
So if a graviton or gravitational wave,
Right.
the graviton would be
Would
the
be the particle.
version of the wave.
Right.
If it washed over me or passed through me, I want my heart to participate in that. I got a cool explainer.
Uh-oh. You're excited. That doesn't happen normally.
Searchlights.
okay.
So this must be a good one.
Extra good.
Yeah.
Okay, ready?
What is it?
Okay. You ever see Hollywood searchlights?
Yes.
Okay.
Because they
We all
shoot a
seen
shaft of
searchlights.
light into the air.
Have you ever looked at one?
A searchlight?
Yes.
No.
No, not directly in it.
Oh, okay.
Just from the
From
side.
the distance, yeah. They're,
You look from the side, and it goes up and up and up, then it stops.
yes.
Have you ever noticed this?
Yeah. Even from a distance, what happens is, because they do it every year for 9/11.
Yes, we do.
Yes.
Yes. What they do is, for people who don't know, on 9/11, in honor of 9/11, because this is New York City. We're here at my office at the Hayden Planetarium. We're now 4 or 5 miles north of Ground Zero. They have 2 huge spotlights.
Yes.
And each go vertically up.
Right.
Creating
the ghost of the towers that went down.
Yes,
Right.
yes. And so just as an homage. To each of the towers.
And so I live in Jersey, and I live pretty much on the river where you can see the installation. And what's cool is there's these 2 shafts of light that go up, but then they disappear into nothing at the very top.
Right, there is a top
There's
to
a
the
top
column of light.
to the column of light.
Right.
Yeah, which is, kind of wild.
It's kind of wild.
Yeah.
Okay. There's a reason for that.
Oh, really?
There's a physics reason for that. If I put you 20 miles
So he's saying the searchlight ends at some point, or you can't see it, and he's probably going to explain that now.
away on the horizon,
Okay.
and I aimed the beam of light at you,
All right.
you would have no trouble seeing it.
Nope, not at all. Especially a searchlight.
Whereas if I point it straight up and you're down here and you're looking, it has an edge.
That's wild.
First of all, you only see the beam because there's stuff in the air, pollen, dust, water vapor, that reflects light out of the beam to your sight line.
A bit like a rainbow where the light enters the water droplets and it refracts or reflects. This is similar. You need to have, for what he's saying is, you need to have some sort of pollution in the atmosphere so the light can reflect, right?
Okay.
Think about that.
That's good.
This is why the phasers in Star Trek, you always see the side view of the Enterprise sending phasers out front. By the way, I never knew why the phasers weren't parallel to each other. They were at an angle.
yeah, always at an angle.
That was a little weird to me.
Yeah.
But if you're looking at a light beam go sideways, you can't see the light beam because the light beam is going the other direction, and it is empty space. They turn on the phasers, it would be nothing for you to see from the side. Unless they get chalk dust.
Right. And pop, pop, pop. Right.
Pop, then you'd see the
see the beam.
because the dust particles are reflecting it back to you out the side of the beam.
Okay.
Okay?
Gotcha.
There's a scene in Star Wars Force Awakens where they have the diabolical Death Star that can kill 8 planets at once or whatever, rather than just one.
Yeah.
Okay? The engine revs up, and these light beams come out, laser power light beams, each aimed for a planet. And it takes out all the
I haven't
planets
seen
in
this
the
film, by
star
the way.
system. Okay? They show people on each of those planets watching the light come to them.
Right.
No, they would have
You have
no
no
idea.
idea.
They would have no idea it was en route. That's why you can see the beam at all. If we were in a total vacuum,
Right.
you would not see anything, and searchlights would be pointless.
So is he saying in space, in total vacuum, you can't see it, but on Earth you can because of pollution? Is that what he said?
Interesting.
Okay? By the way, in the desert where there's less water vapor and less pollen, there's still sort of desert dust. And so you can work with desert dust. But if us were very calm, then the beam would be hardly visible going up. You'd see the base of the light, but the beam would be very hard to see. All right. There's something called the inverse square law of light. So, how bright is a light? If you're twice as far away, it's 1/4 as bright.
Gotcha.
3 times as far away, 1/9 as bright.
Gotcha.
4 times as far away,
1/16.
1/16. So this beam is dropping off in intensity as 1 / distance squared
Gotcha.
from the ground,
From the ground.
from its source. The light gets twice as high up.
Right.
It's only 1/4 as bright at that point. If you're looking down at it, it's 1/4 as bright, 1/9 as bright, 1/16 as bright, 1/25, 1/36. It's getting dimmer and dimmer and dimmer as it ascends.
Right.
Okay? However, you're not looking directly at
it.
the light.
Right.
You're looking at light that reflects back to you from the crap that's in the atmosphere.
Right.
Okay.
So, the light coming back to you also drops off as 1 / distance squared.
I see.
Combine them, the brightness of the beam drops as 1 / distance to the 4th power. So, if it's 3 times higher up, that light is 1/9 as bright there, and it's 1/9 of that 1/9 as bright to you on the ground.
Right.
It's 1/81st as bright.
Look at that.
So on the ground, the light is dropping off exponentially. And there's a point where your cone can't detect it.
We can't, right. There's light there. You're just not going to be able to see it.
Is it infinite though? Is it you just can't see? Is that what he means? So let's say someone's turned on a searchlight and then it's going up in the sky, and he's saying it's just infinite. It keeps going up, but you can't see it because of this law. It just sort of diminishes, drops in intensity, but it's there, you just can't see it. Is that what he's saying? Is there but you can't see it? Or is he saying it's not infinite, it has to sort of get dimmer and dimmer as it goes up in the atmosphere, and then eventually there's an end to it? Let me know in the comments.
Because you're relying on the light reflected
off
off
of
of crap coming back to you. Whereas the person in the beam, it's a simple one over, it's still getting dimmer and dimmer, of course, but it doesn't have this added effect of having to reflect back to you. So all search beams look like they come to an abrupt stop. It rapidly drops below the detection limit of the rods in your retina.
Wow.
Every beam of light going up will look like it has I have a laser that I use to point out the night sky. It looks like it stops. Yet, if you're 60 miles away, you'll be able to see the laser.
Oh.
When was the last time?
Okay, I see now. So so in the end, I guess Neil sort of clarified. He said he's got a laser beam, he points at the sky. People around him, near him, will see it drop off, but then if, like he said, if Chuck was 60 miles away and then he had a look at that laser beam that Neil was pointing up in the sky, he'd be able to see it. So that means it just keeps going up. That's really interesting. A couple of good examples: rainbows and searchlights, and of course the example of bench press in the gym. So yeah, new things to learn every time I watch Neil and Chuck and all the other guests and Brian. There's always something new to learn. Let me know in the comments what you think of these examples. See you later. Bye bye.